Assalamu alaikum and good morning. Today we're going to start with a new topic. This would be the second last topic of your AS syllabus. It falls under the inorganic chemistry and it is topic number 11 where we will be covering group 17, or you may have previously known it as group 7. Group 17 are the halogens, basically your fluorine, chlorine, bromine, and iodine, except astatine. Astatine is not considered as a part of group 17, which is your nonmetals. Okay, they're all nonmetals except astatine. So we will be looking at just the four members, which is from fluorine down to iodine. They are called the p block elements because the last outermost subshell being filled is the p orbitals or the p subshell. So you can see that for fluorine, chlorine, bromine, and iodine, they all end with the same number of electrons in the s orbital and the p orbital. The only thing that's different for each element is the principal number or the shell number. As you all know, that at room temperature, they exist as diatomic molecules. So whenever we talk about fluorine, chlorine, bromine, or iodine, it should be automatically instilled to you that they exist as a diatomic molecule, which has the formula F2Cl2Br2I2. Now, for this topic, it is quite similar to the previous one, which is topic number 10, which covers group 2. They are mostly descriptive. No calculation. You have to memorize the trend, you have to memorize the equation, the observation, and they're quite self-explanatory, in which case it means that you should be able to understand them just by reading them, okay? But I will try to help with the parts where I think need a little bit of explanation. So I'm going to go really fast, but just make sure that whenever you need to fill in on your notes, please just pause the video and just copy things down, okay? Please do not leave your notes blank. The first learning objective is looking at the physical properties, the trend of the physical properties for your elements. We will be looking at colors and volatility. You have to describe the trend and explain it, okay? So the colors of the halogens, they are getting darker as you go down the group. So all you have to do is to describe and basically memorize the colors, bearing in mind that fluorine and chlorine are gases, bromine is a liquid, and iodine is solid. And it sublimes really well. That means it turns from solid to gas, skipping the liquid state. Okay. Here's some trends of the physical properties of group 17 elements, where you are given the atomic radius, the melting point, and the boiling point, as well as the color. Volatility refers to how easily a substance can evaporate. So basically, elements or molecules with low boiling point, we say that they are very volatile. Okay, they turn into gas easily. All right, so by looking at the boiling point, you can see that the boiling point as you go down the group is increasing. That means it gets more and more difficult for them to turn into a gas. So that means the volatility of group 17 decreases as you go down the group. What is the reason behind this? Since volatility is related to the boiling points, you have to go back to the factors that affect the boiling point of your molecules. And going back to topic 3 and 4, since all your group 17 elements are simple molecular structures, that means during boiling process, we are only breaking the intermolecular forces. And the intermolecular forces that's present in or between the molecules of your group 17 elements is the ID force, okay? And if you still remember from topic 3, one of the factors that affect the strength of your ID force is the number of electrons. So you would imagine as you go down the group, you have bigger number of electrons, therefore your ID force gets stronger, hence you need a lot of energy to break the ID force between the molecules. That is the reason why volatility decreases as you go down the group. Okay, this is just to recap on the origin of your ID force. So the conclusion is, going down the group, the ID force increases due to an increased number of electrons in the molecules, which means that the volatility decreases for your elements. Moving on to the bond strength. Next learning objective, describe and explain the trend in bond strength of the halogen molecules. Now, wait, I hope I didn't go too fast. Okay, so you can screenshot this reason. Sorry, you can screenshot this slide, and then I will move on to the next one, which is the bond strength. Bond strength is the same as bond enthalpy. It is the energy needed to break 1 mole of a covalent bond. Basically, the bigger the number of your bond enthalpy or your bond energy, the stronger your bond is. Okay, so how do you define a bond? Covalent bond is the attraction between the nucleus and the pair of shared electrons. Okay, so it's the attraction between this nucleus and the bonding or the shared electrons, right? So the bigger the size, as you can imagine, if you just compare these two example, fluorine molecule on the left and iodine on the right, you can see that in the fluorine molecule, the distance between the nucleus and the bonding electrons is smaller compared to the distance between the the nucleus of iodine and the bonding electrons. So that means the closer this distance is, the stronger the force or the stronger the covalent bond is. The further away the nucleus and the bonding electrons, the weaker the covalent bond is. Okay. So this is the explanation. Going down the group, it has something to do with the atomic size. Okay, when you come to the exam, it is not enough for you to just write, oh, the reason why the bond strength is getting weaker as you go down the group because the atomic size is getting bigger. Okay, you have to mention that the bonding pair or the bonding bonding pair of electrons in the covalent bond get further away from the halogen nucleus and therefore less strongly attracted to it. So that means it's easier for you to break the bond, easier for you to break the covalent bond because of the weaker attraction. Next, we're going to move on to the trends and chemical properties of group 17. This will be a lot because most of the time it will be talking about equations. There are some pattern that you need to learn, but it will be generalized later on. Okay, so you will see what I mean by this. First, we want to describe the relative reactivity of the elements as oxidizing agents. So halogens in general, your fluorine, chlorine, bromine, iodine molecule, they act as oxidizing agent. That means they oxidize another species where itself gets reduced. Okay, so we want to look at this reactivity, the strength in the oxidizing, the strength of the oxidizing agent, sometimes called the oxidizing power. Okay, it just means that if it has an oxidizing power, it is a good or a strong oxidizing agent. Okay, as for halogen atoms, unlike the group 2 metals, when they are involved in a reaction, they tend to lose electrons. Okay, but your group 17, your elements, they do the opposite. They gain 1 electron to complete their octet when reacting with metals. Okay, so as you all know, nonmetals will react with metals. So nonmetals tend to gain electrons. So we have to think about how easy or how difficult does it get for them to gain electron as you go down the group. okay? And it turns out that it gets more difficult to gain electrons as you go down the group. Unlike your group 2 metals, it gets easier to remove that 2 electrons in the outermost shell, okay? Right, so we say that because the reactivity decreases, the oxidizing power or the oxidizing strength also decreases down the group, all right? Since halogen needs to gain 1 electron, we categorize them as an oxidizing agent. And you have learned already in topic 6 recently that oxidizing agents tend to accept electrons. Okay, the reason is because oxidizing agents will get reduced. And for the halogens to be reduced, they need to gain electron. Okay, remember your oil rig, oxidation is loss of electrons, reduction is gain in electron. Okay, so what happens? So I've already mentioned here, halogens will oxidize the other species. Usually they will react with metal, so it will oxidize metal, where the halogen itself become reduced. They get reduced, okay? All right, so this has already been mentioned as well. The reason has to do with the size as well, okay? So going down the group, the atomic radii of the elements increases, okay? The size is getting bigger, right? And remember, these halogens want to gain electrons. So in order to gain electrons, they need to have a power of attraction. You don't just grab the electrons by yourself without having any attraction, okay? So the attraction, the pulling force is coming from the nucleus. So it's the same idea. If your nucleus is close to the outermost shell, that means you are able to pull an electron. You are able to attract an electron to you. However, if your size is bigger, your nucleus is further, that means the attraction to gain an electron is less or weaker. Okay, so that's the idea of the reactivity of the halogen. It's all about their ability to accept an electron, and it has something to do with their size, okay, which is the atomic radius. So that goes in the reasoning, okay? It has something to do with electronegativity as well, okay? How strongly an atom attracts electrons towards itself in a covalent bond. So it's the same, whether you're talking about halogens reacting with a metal, in which case they are forming ionic bond, okay, or they react with another nonmetal, in which case they form a covalent bond. So you talk about electronegativity. Right, so you can pause here if you want to copy this down. Next, we move on to the first reaction to show the reactivity, okay, the decreasing power of the decreasing oxidizing power of these halogens in a displacement reaction. So I'm not going to go into details of a displacement reaction, as I'm sure you have learned this already previously, okay? So the idea of displacement is a more reactive halogen will displace. Another word for displace is replace a less reactive halides. Okay, so I need to point out halogen and halides are two different things. Halogens is the molecules like F2, Br2. Oh, it should be chlorine first. Oops. So, okay. Cl2, Br2, and I2, whereas halides is your anion. Okay, halogen is the molecule, halides is the anion, F minus, Cl minus, Br minus, and I minus. Okay, be careful with the formula. It's not F2 minus, right? Halides are a single ion. It's a monoionic, okay? And it has a charge of -1. So with this said, the stronger or the more reactive halogens will be able to replace the weaker halides. Okay, so that means chlorine will displace bromide and iodide. Bromine will displace iodide ions. Iodine cannot displace anything because iodine is the less reactive. Okay, why do we not talk about fluorine? Because as usual, fluorine is the top member of group 17, which behaves differently. I mentioned this in the previous topic already. Usually the top member and the most bottom member, they're two extremes and they don't usually follow the pattern. Okay, so we stick to it. We stick with chlorine, bromine, and iodine. So here's an example. On the top heading here is your halogens. Okay, and then on the side is your halides. Now your halides needs to come in a reagent. Okay, so you don't just add chloride ions just on its own. It's not stable. Chloride ions need to be counteracted with a cation. Okay, for example, potassium chloride or sodium chloride. So your ion needs to exist as an ionic salt, for example. Okay, so your halides come in the form of potassium chloride, potassium bromide, and potassium iodide. So in solution, they actually exist as K plus and Cl minus. Okay, K plus and Br minus, K plus and I minus. Okay, right. So what happens is chlorine, aqueous chlorine, is pale green in color originally, pale green solution, whereas bromine is yellow colored solution, very light. You would, why is it not brown, as I mentioned earlier on? Because that's bromine Br2 as a liquid. Br2 as an aqueous is the bromine dissolved or diluted in water. So you would imagine the brown color would become very, very light when you add water. Okay, and your iodine would be brown solution. Okay, as solid it is purple or even black, but when you dissolve it in water, it appears as brown solution. Okay, whereas your halides, sorry, all your halides are colorless. Please bear this in mind. They are all colorless. Okay, so students always think that potassium chloride is just like chlorine, green in color. No, potassium bromide is colorless, not yellow. Potassium iodide is also colorless, not brown. So how do you know, how can you confirm when there's a reaction happening? Because the only indication for you to know whether a reaction has happened or not in this displacement reaction is by looking at the color change. Okay, so how do we read this table? Okay, so you see here, chlorine is reacting with potassium chloride. Chlorine is reacting with chloride. There is no reaction. Okay, so no reaction means the pale green stays as pale green, no change in color. All right, next, chlorine reacts with bromide. Chlorine is a stronger oxidizing agent. Bromide is a weaker. I wouldn't call it an oxidizing agent because bromide is actually a reducing agent, but I'll leave that for later. Okay, so chlorine can actually displace bromide. So what happens is that your pale green, which contains bromine, reacts with the potassium bromide to form bromine. Okay, so bromine has been formed here. That's why you see a yellow solution. Okay, so that yellow solution is due to the formation of aqueous bromine. The reason for this is the chlorine has displaced the Br minus. Okay, next, chlorine reacting with potassium iodide. Chlorine is a stronger oxidizing agent. Iodide is weaker. Okay, so what happens? Chlorine can displace iodide to form iodine. So here again, the brown solution is due to the formation of aqueous iodine. Right? Next row and next column. Bromine cannot displace chloride because bromine is a weaker oxidizing agent. Right? Bromine does not react with bromide, no reaction. Bromine can react with iodide because bromine is a stronger oxidizing agent than iodine. Therefore, what happens? The iodide will be displaced and iodine aqueous will be formed. Okay. Whereas iodine does not react with anything, so it stays as brown color. Okay, so there's no reaction. So please take note, no reaction happening. The reason why you see color is actually just the original color of your halogens. Okay, so iodine is the weakest oxidizing agent and it does not displace any of the halides. Okay, right. Okay, so that's should be everything that I want to explain on this table. If you want to copy down, please take a screenshot or pause this video. Here is the equation for the reactions that I mentioned just now. Okay, so chlorine displacing your bromide is here. Okay, that's the reaction. You see the color change as green to brown. The others are colorless. Please take note that your halides are colorless. Okay, all your halides, bromide, chloride, iodides are colorless. Chlorine displacing iodide is this second reaction. Okay, so you go from green to brown. Sorry, it is not brown for bromine. It should be yellow. Oops. And lastly, bromine displacing iodide is this reaction where you see yellow turning into brown solution. Whereas this all those three halides are colorless. Okay. Right. So the idea is a more reactive halogen will displace a less reactive one from its compounds. Next is another reaction to show to show the halogens reacting with hydrogen. The observation should be able to tell you the trend or the pattern in the reactivity of the halogens. So you have to describe the reactions of the elements with hydrogen and explain their relative reactivity in this reaction. Okay, so you're given the general equation for the reaction of hydrogen with halogens. When halogens react with hydrogen, they form what is called a hydrogen halide. So hydrogen halides is this: hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. So these are all examples of hydrogen halides or sometimes also called halogen hydrides. Okay, they're both the same name. So last time I think I got this confused. Yeah. Okay, so the observation is you can see that from the top member of group 17, which is the most reactive and the strongest oxidizing agent, it reacts explosively even in cool, dark conditions. No energy in the form of heat, no energy in the form of light, and they react explosively. That's how reactive fluorine is. Maybe that's why we don't look at fluorine that much. Okay. Next, it's with chlorine, it still reacts explosively. Okay, but you need sunlight, you need energy in the form of light. With bromine, you need to heat them in order to get them to react. So that means some form of heat energy is required for this reaction to happen to form your hydrogen bromide. And then lastly, your hydrogen and iodine, they form an equilibrium mixture on heating. That means whenever you form a hydrogen iodide, the hydrogen iodide would want to go back and dissociate itself into the elements, okay, into its original form, which is hydrogen and iodine. So that means you will not get a lot of hydrogen iodides at equilibrium, okay? So what's the reason for this? It all comes back to the reason why the reactivity of halogens are decreasing as you go down the group, okay? It all goes back to the oxidizing agent of these halogens decreasing in power or decreasing in strength as you go down the group, and that has to do with the atomic radius, the size, okay? Because everything else is the same. They have the same charge. They need to gain 1 electron to obtain an octet structure in a reaction. The only thing that's different between fluorine and iodine would be the size, okay, among other things like the mass and the number of electrons. But the most important point is that the size, the atomic radius. Okay, so what happens? Atomic radius increases, and then more shielding as you go down the group. So when distance increases, shielding increases as well. The power to attract or the power to gain electrons get weaker. Okay, hence oxidizing power decreases. So remember, oxidizing agent is all about gaining electrons. Reducing power is all about losing electrons. So this goes hand in hand with decreasing electronegativity as well. Electronegativity has the same idea. It's about the attraction between the nucleus and the bonding electrons or the bonding pairs. Okay, thermal stability of hydrogen halides. You've all looked at thermal stabilities in group 2, which is topic 10. Thermal stability means how stable your molecule is when it is heated. Okay, so describe the relative thermal stabilities of the hydrogen halides and explain this in terms of bond strengths. So this time we are going away from your elements. We are now focusing on the hydrogen halides. So what are my hydrogen halides? HF, HCl, HBr, and HI. Okay, so thermal stability refers to how well a substance can resist breaking down when heated. A substance that is thermally stable will break down at high temperatures. That means if you need a lot of energy to break down the molecule, that means this molecule is stable to heat. Okay, we say it's thermally stable. All right, so what happens? What's the trend? Okay, so basically, the most stable hydrogen halides is your hydrogen fluoride. Okay, so they do not break down, they do not decompose, and also HCl. Okay, they are stable to heat, whereas your hydrogen bromide will decompose slightly. So how and what will it be broken down into? Your hydrogen bromide will be broken down into hydrogen gas and bromine gas. Okay, so you will see a very slight browning, brown gas being produced, which indicates the bromine gas. Okay, whereas hydrogen iodide is the most unstable. That means you don't need a lot of energy. You don't need high temperature to break down your hydrogen iodides into hydrogen and iodine. All right. So this is now on page 4. Okay. Reason. What's the reason for the thermal stability decreasing as you go down the group? Because thermal stability involves breaking down the hydrogen fluorine, the hydrogen halides bond. We want to look at the bond strength of this hydrogen and the halogen. Okay, so the reason for thermal stability is again something to do with the size. As the size of the halogen increases down the group, the hydrogen-halogen bond, HX bond, where X stands for either fluorine, chlorine, bromine, and iodine. Okay, the bond becomes longer as well. Okay, why? Because of the distance when we measure the length of the covalent bond, we're actually measuring the distance between the nucleus of the two atoms. Okay, so since iodine is bigger, so that means the length between the nucleus is also bigger, right? So that's why you would imagine the bond length increasing. So longer bond means weaker bond, and therefore it is less stable to heat. Okay, now if you look in your, I'm not sure if they do give bond length in your data booklet, or is that from the older one? Okay, so you can see that the weaker or the smaller the bond energy is, the bigger the bond length is. Okay, so that's the trend. That's the observation. So these things you need to remember. Okay, whereas the bond energy is given to you in the data booklet. So remember this reason. Copy it down to your notes. Please screenshot if you need to, if you need time. Next is halides. So we are going away from the halogens. We are still in the hydrogen halides. Okay, now we want to look at the halides. So just now I mentioned that the halogens are oxidizing agents. Okay, the halides, which is the anions, is the opposite. So they act as reducing agents. Okay, so describe the relative reactivity of halide ions as reducing agent. So please remember this. Okay, halogens act as oxidizing agent. Halides react as reducing agent. Okay, why? Because of how they behave in a reaction. Right, you will see later on that halides tend to lose electrons. Okay, yes, lose electrons. They reduce other people with themselves being oxidized. Halides are reducing agents which lose an electron when they react. The halides show increasing reducing power as one goes down the group. So they also have opposite relationship. For the halogens, the oxidizing agent or the oxidizing power decreases as you go down the group, where iodine is the least reactive, fluorine is the most reactive, or we say the strongest oxidizing power. Okay, so it is the strongest oxidizing agent, whereas the iodine is the weakest oxidizing agent. But for your halides, it's the total opposite, okay? Your reducing power increases as you go down the group. So iodide is the strongest reducing agent, whereas fluoride is the weakest reducing agent. Okay, so if you just remember one, halogens, and then that means the halides has the opposite property. Okay. Okay, so this can be clearly demonstrated in reactions of the solid halides with concentrated sulfuric acid. Okay, so that's the reaction that we're going to look at to prove the power of the reducing agent, the power of the halides as reducing agent. Okay. Okay, so that means, right, because halides reduce other people, they themselves get oxidized. Okay, and how do we learn this is by looking at how easily these halides are being oxidized. Okay, so I may need to add that again. Halogens oxidize other people, itself gets reduced. Whereas halides reduce other people where itself gets oxidized. Okay, next slide. So explanation for reducing power of halides down the group. So always everything, every trend, every pattern needs to be supported by the explanation. Why is it that as the halides go down the group, they get stronger, they have stronger oxidizing power, reducing power, okay? There, I've confused myself. So as mentioned earlier, halides are oxidizing agents. That means they themselves, halides are reducing agent and they themselves get oxidized. Oxidation is the loss of electrons. Okay, so that means reducing agent loses or donates or give away its electrons, and the power increases. That means it gets easier to lose electrons as you go down the group for the halides. I try to go really slow so that I don't get or say the wrong thing, which I know I will because I've already done it like 3 times in a few seconds. Okay, so when halides lose electrons, they always lose electrons from the outermost shell. Okay, and again, when you lose electrons, you don't just give away like that. There is an attraction that's holding these electrons around an atom. This attraction comes from the nucleus. Okay, so if you imagine losing an electron from fluorine, okay, which I will use a different color so you can see, green, okay, so you see the distance between the nucleus and the outermost shell there is that much, okay, that's the distance. Whereas for iodide, when you lose electrons from the outermost shell, the distance between the nucleus and the outermost shell is that much. The bigger the distance is, the weaker the attraction. Just like magnets, when they're really close, the attraction is really strong, but when they're far, the attraction is really weak. So because of the size of the iodide again, this attractive force between the nucleus gets weaker as you go down the group. That means the electrons are being less strongly or less tightly held to the nucleus or to the atom. So it becomes easier to lose these electrons as you progress from fluoride to iodide. Okay, so that's being explained here. Ions get bigger outer electron is further from the nucleus. There's also shielding, which I did not mention, but you should mention shielding whenever you talk about the distance because they go hand in hand. So the outer electron is lost more easily, okay, because the pull from the nucleus or the attraction from the nucleus gets weaker. So if you don't like the word pull, it's the same concept as attraction. All right, so you already know how to explain why oxidizing power decreases as you go down the group of halogens and why the reducing power increases as you go down the group of the halides. So please be careful with the species that you are talking about here. Are you talking about the halogens or are you talking about the halides? Because these two are different and they have different characteristic as well. As you can see, one is an oxidizing agent, the other one is a reducing agent, and their relationship is the total opposite. Okay? Right, so how can we look at the power or the increasing power of the halide ions? How can we prove that halide ions gets more powerful as you go from fluoride to iodide? Okay, so there are two reactions that we can look at. The first one is the reaction of silver nitrate followed by aqueous ammonia. This reaction is a very familiar reaction to you. You have done it many times in the lab. The second reaction, concentrated sulfuric acid, is not something that you have done, but it's also something that students don't like to memorize because of there are many equations that you have to memorize. Okay, so that's why students, they always skip this. But I noticed that when this topic comes out in the exam, they will go all out. They will ask you to write down the equations. Okay, but if it happens during your time, your exam, that they don't ask anything about group 17 in your paper 1 or paper 2, then you are safe. Okay, so describe and explain the reactions of your halide ions with aqueous silver ions, followed by aqueous ammonia. Okay, not sure if anyone is already getting an idea of what kind of reaction this is, but this is actually your qualitative analysis test. Okay, this is usually question 3 in your practical, where to identify your chlorides, bromides, or iodides, you add silver ions. Okay, you either use silver chloride or silver nitrates, whichever is available to you in the lab or during the exam. Okay, and then you add ammonia because you want to test for the solubility. Okay, what's the procedure? Right, sometimes you will notice that in your qualitative analysis, they will tell you add a few drops or equal amount of nitric acid. The reason for this is because if there's any impurities, okay, they will form a nitrate salt. And as you know, nitrate salts are all soluble. Okay, so they will not interfere with your test for the halides. So that is the purpose of your nitric acid. Usually we remove, the reason we add nitric acid is to remove impurities. Okay, right, so you will add silver ions, usually silver halide, whether it's a silver chloride or silver nitrate, right? And then you should be expecting a precipitate. Your precipitate can either be white, cream, or yellow. Okay. Now you may think, okay, so if I already know the precipitate is white, why do I need to move on with adding ammonia? Now the problem is because white, cream, yellow precipitate are usually not distinctive. They will look similar. Remember, you always ask me, Miss, is this white? Miss, is this cream? Miss, is this yellow? So they're not distinctive. That's why we ask you to do a further test that is not adding excess, but adding ammonia to your test tube. Because what ammonia what ammonia can tell you is about the solubility of the precipitate. Okay, if the precipitate is soluble in ammonia, that means it would have been a chloride. Okay, if the precipitate is partially soluble, now partially soluble is a very tricky observation because you don't know what partially soluble is. It's in the middle. If it dissolves, then you know for sure that it's soluble. If it doesn't dissolve, then you know for sure it's insoluble. But how do you know when things are partially soluble? Okay, so hopefully when that happens, the color of the precipitate is clear so that you're able to identify that it is a bromine. All right. As for iodide, it is insoluble. Okay, so please understand why we add silver ions, and also please understand why we add ammonia. Silver ions, whether it's silver chloride or silver nitrate, is to form a precipitate. And it's nice when you form precipitate is something that you can observe, okay? And the addition of ammonia is to check for the solubility. Okay, so this is the equation of the reaction of halides with silver nitrate. Okay, so silver nitrate, this works with silver chloride as well. Reacting with your halides, in this case, it's written as X minus. Now, because it is a precipitate, we call it a solid. Your silver halide, AgX, whether it's AgCl, AgBr, or AgI, plus nitrate ion. So your nitrate ion is just your spectator ions floating in that reaction mixture. Okay, so for the ionic equation, they also like to ask you to write down the ionic equation for the formation of the precipitate. Okay, so this is easy. If you are forming silver chloride solid, it just means that you have silver ion plus chloride ion. That's it. If you are forming silver bromide, you start with silver ion plus bromide ion. Silver iodide is made up of silver ion and iodide ions. Pretty simple, okay? But learn this because they like to ask you in the qualitative analysis question. Okay, right, so I've already talked about this, that they all have similar color and really difficult to differentiate them. So if you're wondering what that white precipitate is when you add your silver chloride or silver nitrate, that precipitate is your silver chloride, okay? When you have a cream precipitate, it's silver bromide, and yellow precipitate is silver iodide. So this is just showing you the procedure, so I'll skip that. Okay, so this table is showing you what happens. I think, yes, you have this in your notes, okay? So the equation of the formation of the precipitate is given to you here, and as well as the observation, okay? So when adding ammonia, it depends on the type of ammonia you're adding. Are you adding dilute ammonia or are you adding concentrated ammonia? Okay, so what happens is that your silver chloride will dissolve. Your white precipitate will dissolve in both dilute and concentrated. Your silver bromide will dissolve only in concentrated ammonia, and your silver iodide will not dissolve in either type of ammonia. Okay, so basically what happens is that when they dissolve, complex ions is formed. Now, earlier on in your learning objective, they mentioned that you don't have to learn about the formula, okay? But there's actually a complex, we call it a complex ion. You learn about complex ion next year for your A2 syllabus, okay? Right, moving on is the second reaction, and this is the important reaction. that shows the strength of your halide ions, okay, how powerful the halide ions are as reducing agents. Okay, so basically you will react your halide ions with concentrated sulfuric acid. You have to describe, that means you have to observe, you have to know the observation, you have to explain, as well as write the balanced chemical equation. It is mentioned in your learning objective, so that means you must include balanced chemical equations. You'll see shortly why I mentioned just now students don't like this part, because there are a lot of equations that they have to learn. Okay, so reaction of halides with concentrated sulfuric acid. This time your halides has to come with a counter ions. Okay, so the counter ions can be sodium, can be potassium, can be magnesium. Okay, so usually it's the metal, right? So solid ionic halides. So these are example of solid ionic halides. It's your halides combined with metal ion. React with sulfuric acid to form a hydrogen halide and also sodium hydrogen sulfate. So this is the general equation for the reaction of your ionic halides, which is sodium X plus sulfuric acid, which is a liquid, to form a sodium hydrogen sulfate solid and your hydrogen halides gas. So your hydrogen halide gas are mostly white in color. HCl, when it is a gas, it appears as white fume. HBr and HI will also appear as fume, but you wouldn't observe them here. Okay, so I'll talk about that. The first reaction that we're going to look at is the sodium chloride and sulfuric acid. In your notes, it mentions that this works for sodium fluoride as well. So what happens? Referring to the general equation in the previous slide, sodium chloride will react with sulfuric acid to form sodium hydrogen sulfate, okay, and hydrogen chloride gas, which appears as white fume, right? Because chloride is a weaker reducing agent, the reaction stops there. It does not get oxidized further. Okay, this is not an oxidation reaction. This is more like it's not a redox basically, because the oxidation number of your chlorine stays the same. In NaCl, it's -1. In HCl, it's also -1. Okay, so when sulfuric acid is slowly dropped onto crystals of sodium chloride, you will see white fume producing. That indicates the formation of hydrogen chloride gas. Because the reaction stops here, this is a great practice to produce hydrogen chloride gas. Okay, and the hydrogen chloride gas formed is not a strong reducing agent. That means it cannot reduce the sulfur and it cannot oxidize itself. So no redox reaction occurring. This is different from sodium bromide and sulfuric acid. So following the general equation of sodium bromide and sulfuric acid, you will produce again the sodium hydrogen sulfate, which appears as a solid, and you produce hydrogen bromide gas. However, the hydrogen bromide gas will react further. So what happens? Your hydrogen bromide gas will react with sulfuric acid in this reaction mixture. Okay, you cannot separate them because they're all in the same mixture. So what happens is that further reaction occurs. The hydrogen bromide gas will reduce sulfur in the sulfuric acid to sulfur in the SO2. So you will see that the oxidation number of sulfur will change because it's reduced. That means it should decrease. And the oxidation of bromide, Br atom, will increase. Remember, reducing agent reduces other people. In this case, it reduces sulfur, where itself is being oxidized. Right? So we're going to look at the oxidation number for this reaction, this redox reaction. Okay, so this is the first part of the reaction, which is not a redox. Okay, and then what happens is that you have this hydrogen bromide reacting with H2SO4 to react further. Okay, and you will see a redox reaction occurring. Okay, so let's see. We are now going to look at the oxidation number of the sulfur first. Okay, so if you still remember to how to determine or how to work out your oxidation number of sulfur, remember SO4 2 minus, okay, when you add the oxidation number of sulfur plus 4 times of the oxidation of oxygen, you should get the sum to be equal to -2, okay, because oxygen will have to be -2. That means sulfur would have to be +6. Okay, now you may ask, why does oxygen have to be -2? Because the more electronegative atom usually gets priority of the negative oxidation number. The observation is that hydrogen bromide doesn't have a color, it's colorless. Sulfuric acid is also colorless. Sulfur dioxide is a colorless gas, so pointless, you won't be able to observe anything. And bromine gas, it's red or reddish brown gas. Okay, so that's definitely that is something that you can observe. H2O is colorless. Okay, so what happens is that, okay, I'll move on to the next slide. So in this case, your hydrogen bromide gas is acting as a reducing agent, and your sulfur in the sulfuric acid is acting as an oxidizing agent. So that means sulfur, which has a oxidation number of +6, will be reduced to sulfur with an oxidation number of +4. So here is a reduction process. Whereas your bromide, okay, I will focus on one atom of bromine first. Okay, so in this case, I've got -1. Okay, but there are 2 times, so please be careful. Okay, when I talk about the oxidation number, I am referring to a single atom only. So that's why I write it down as -1. And the oxidation number of bromine in Br2 is 0. Okay, and there are 2 times of Br2. So I go from -1 and -2 to 0. That is an oxidation, because increase in oxidation number increases. Okay, so my observation would be red fumes or reddish brown gas of bromine. I will not observe the white fumes of HBr, because the moment I have HBr, it will immediately react with the sulfuric acid. It will reduce the sulfuric acid. Okay, but this doesn't happen with hydrogen chloride, because hydrogen chloride is not a strong enough reducing agent. It cannot reduce the sulfur in the sulfuric acid. Next is sodium iodide and sulfuric acid. Same procedure in the first part. Your sodium iodide will react with sulfuric acid to form a solid sodium hydrogen sulfate, and you form a hydrogen iodide gas. Now, this hydrogen iodide gas, as we all know, is the strongest, the most powerful reducing agent. So it will immediately, almost vigorously, instantaneously react with the sulfuric acid. Okay, so you can see the reaction is even crazier. Okay, so hydrogen iodide will combine with sulfuric acid to form all these different things, there are three reactions showing you how crazy, reactive, or powerful your hydrogen iodide is. Okay. So when hydrogen iodide is produced, it reduces the sulfuric acid to a mixture of products, including sulfur dioxide, which is the colorless gas. Sulfur here is a yellow solid, okay, which I did not include that. I should include. Sulfur is a yellow solid. And hydrogen sulfide. Hydrogen sulfide is a colorless gas, but with a strong smell. It has a bad egg smell. Okay. Not sure if you have ever smelled bad eggs before, but it's really bad. Okay. Right. So if you are going to ask me, yes, they can ask you to write down the reaction, and yes, they expect you to be able to write it down. So these are the three different reactions that can occur between the hydrogen iodide with sulfuric acid, and most likely that all three will happen, because that's just how strong and powerful iodide is as a reducing agent. Okay, the other product is just water. You don't really observe water because it's a colorless liquid, but the others, iodine, you will observe it as a purple vapor. Okay, it's a purple gas. So if you look at the oxidation number here, you can really see that the sulfur is being reduced. Okay, in the first reaction, sulfur is being reduced from +6 to +4. So that is a decrease in 2. So your oxidation must also increase by 2. So -1 is the oxidation number of your iodide. Since there are 2 lots of it, I would just write down in bracket 2 times. Okay, and then there are 2 iodine atom in an iodine molecule, so I just multiply it by 2. In the second reaction, where your sulfur in the sulfuric acid has an oxidation number of +6, and then in the hydrogen sulfide gas, it has an oxidation number of -2. So that is a decrease in 6 + 2, 8. Okay, so there's a drop in 8 oxidation number. Your oxidation must also be increased by 8 units. Okay, so iodide is -1, but since there are 8 atoms of iodine or iodide, so you multiply it by 8 and same thing. Okay, you go from -8 increase to 0. So that's an increase in 8. So the oxidation numbers are increasing, and it is offset by the decrease in oxidation number as well. And the last reaction, you will see that your sulfur in the sulfuric acid goes from +6 to 0. So that's a decrease, that's a reduction in 6 units. So you would expect the oxidation should increase by 6 units as well. Again, your iodide in hydrogen iodide has an oxidation number of -1. Since there are 6 lots, you multiply it by 6, and it's going from -6 to 0. That's an increase in 6 units. Okay, so just label oxidation for each of this process. Okay, so I've already color coded them. Oxidation, and these 3 equations, reactions, are showing the oxidation of your hydrogen iodide, and also the reducing of sulfur. So what hydrogen iodide is doing is that it reduces sulfur to different things. Okay, so sulfur is reduced to SO2, sulfur in sulfuric acid is reduced to H2S, sulfur in sulfuric acid can also be reduced to sulfur as a solid powder. Okay, it's a yellow solid. So if I tabulate this and summarize the reaction of the sodium halides with sulfuric acid, you can already see that sodium chloride is the least reactive, okay? Well, it's not sodium chloride. Actually, I'm looking at the hydrogen halides, okay? So it's the hydrogen halides. Since there's no further reaction, hydrogen chloride is the weakest reducing agent, or we say that it has the weakest reducing power, whereas hydrogen iodide is the strongest reducing power, and it has the strongest, it is the strongest reducing agent, okay? So that's just to summarize it. Make sure you read them and understand them. Don't get them confused because halogens and halides have opposite relationship. Last part of this section is disproportionation, is a type of reaction that oxidizes and reduces the same molecule but different atom. Okay, so we're going to look at the reaction of chlorines with aqueous sodium hydroxide. Let's see. I need to check my notes for this. I don't want to get my equation wrong. Okay, so first we're going to look at the reaction of chlorine with cold aqueous sodium hydroxide and hot aqueous sodium hydroxide. You have to look at the changes in oxidation number, and you have to recognize it as a disproportionation reaction. Okay, so disproportionation reaction is the name for a reaction where an element is simultaneously oxidizes and reduced. I'll look at this later on when we look at the example, okay? So chlorine will behave differently when it reacts with aqueous sodium hydroxide in cold temperature, about 15 degrees Celsius, and in hot temperature, about 70 degrees Celsius, okay? So this works with chlorine, bromine, and iodine as well. So if you start with chlorine, you would imagine chlorine to be pale solution, pale green solution. Okay, pale green solution. So your observation would be to see colorless. Your pale green solution will be decolorized. Okay, so what's different between these two? Both of them will produce sodium chloride. The only difference is in the formation of the chlorate ion. We call this the sodium chlorate. Okay, this is also called a sodium chlorate. The only difference is in the oxidation number. Okay, the other product you produce would be water. And if you were to ask me, yes, you have to memorize this equation. Right, so let's have a look at the oxidation and reduction process. Okay, first we look at the cold when chlorine reacts with the aqueous sodium hydroxide in a cold condition, for example 15 degrees Celsius. Okay, so in this molecule there are two chlorine atoms, okay, but we are looking at the same molecule, right? So what happens? The same molecule is being reduced and being oxidized at the same time. This can happen only because in one molecule of chlorine, there are two chlorine atoms. The same atom cannot be oxidized and reduced at the same time. The same molecule or the same element can be, but the same atom cannot. Okay, so where did I get my chloride ions from? It comes from the sodium chloride earlier on. This is the ionic equation. I hope you all know how to write down the ionic equation. Basically, you just break down your sodium hydroxide into sodium ions and hydroxide ions. Your sodium chloride, break it down into sodium ions and chloride ions. And then your NaClO, so that's the only thing that I would want to add, is made up of sodium ion and ClO minus. This is called a chlorate 1 ion. That means the oxidation number of the chlorine in the ClO minus is 1, +1. Okay, so let's have a look. Okay, so I'll just write down that you can actually break them down into ions so that you know how to work out the ionic equation. Okay, the ionic equation is given here. So what happens in a chlorine molecule? There are 2 chlorine atoms. Okay, both of them has an oxidation state of 0, so I will multiply it by 2. However, one of the atom will go into Cl minus, so you go from 0 to -1. The other chlorine atom, maybe I should label it as chlorine A and then chlorine B. Okay, so chlorine B, the second chlorine, will be oxidized into +1. Okay, chlorine with an oxidation number of +1 in a ClO minus ion. Okay, so how do I work out the oxidation number of ClO, the chlorine in ClO minus? I have to add chlorine and oxygen. I have to add the oxidation number of chlorine and the oxidation number of oxygen, and I should get -1. As we all know, oxygen is -2 because it is the more electronegative element. So chlorine would be +1. Okay, how to work out oxidation number. And that's it. The same chlorine molecule is being reduced and oxidized in the same reaction. Okay, so that's just the explanation. The half equation for the oxidation reaction is, let's see. Okay, for oxidation reaction, it's half Cl2 plus 2OH minus to go into ClO minus plus H2O. Since it is oxidation, we lose electrons, so your electrons will appear on this side. Whereas your half equation for the reduction is when you gain electrons. So it's half Cl2 plus E minus to form Cl1. Okay, and the oxidation number is 0 here, +1 in ClO minus, 0 in chlorine, and -1 in Cl minus. Okay, so you notice that for my oxidation, I'm using half a chlorine molecule, so that means 1 chlorine atom. Likewise, for the reduction, half of a chlorine molecule, which means it's just 1 chlorine atom. Next is the reaction in hot alkali, same thing. This time, you have your chloride ion as ClO3 minus. So this is different ion from the previous one. Okay, the previous one was chloride 1 ion, which is ClO minus ion. Now it's ClO3 minus ion. Same thing. This time, I've got 3 times 2. I have 6 chlorine atoms. Okay, 5 of them is being oxidized from 0 to +5 in chloride ion, and 1 of them is being reduced to oh, sorry. It's the other way around. 5 is being reduced to -1. Okay, so 5 times, and 1 is being oxidized to +5. So this is again an example of disproportionation reaction. The same element, okay, chlorine, is both oxidized and reduced, but different atoms. So that's the most important thing. Okay, so I will not show you again how to find the oxidation number of chlorine in the chloride ion. You can work it out yourself. You should get +5 as your oxidation number. I will show you the half equation for the oxidation reaction, which is half Cl2 plus 6OH minus to form ClO3 minus plus 3H2O plus electrons. Okay, so here we are only using one chlorine atom, so we go from 0 to plus 5. So that means the oxidation is by 5 units. The reduction would also must be by 5 units. Let's see. Reduction reaction is 5/2 Cl2. So if you cancel this out, that means you have 5 chlorine atoms plus electrons to form 5 Cl minus. So the oxidation number is 0 and -1. Okay, don't forget because there are 5 of them, so I multiply it by 5. Okay. Lastly is the chlorination of water. Explain, including by use of an equation, the use of chlorine in water purification to include the production of the active species HOCl and ClO minus HOCl and ClO minus ions. Okay. So you just have to learn the equation for this one. Same thing, the chlorine here is being reduced. Okay, you go from 0 in HClO, it is oxidized to +1. In HCl, it is reduced to -1. So HClO is made up of H plus and ClO minus. Okay, so the uses of this reaction is to kill bacteria. Okay, so please copy down this part, and that's it. We're done for this topic. Okay, so they're all wordy and equations, so that's why I've decided to go really fast, really quick, so that we don't waste a lot of time. So it's better that we use the time for exercise. Okay. As usual, there will be questions for you to answer in the forms. Thank you, everyone. Assalamu alaikum and goodbye.